Welcome back to the bare metal programming series. So far, we have been working with the ATMEGA2560 and the Arduino Mega, blinking the LED in pure C, then in pure assembly, and building makefiles for both. Today, we begin our journey with the ATSAM3X8E, the ARM Cortex-M3 microcontroller, and the Arduino Due R3. Alright, before we bring this microcontroller to life, let's get familiar with it and understand what we're working with. The ATSAM3X8E is a 32-bit ARM Cortex-M3 running at 84 MHz, very different from the 8-bit AVR. It has a new memory map, startup sequence, clock system, and in ROP architecture. Everything changes, and we'll build everything from scratch. Just like on AVR, we control hardware directly through memory mapped I/O. But now, addresses are 32-bit, peripherals are more complex, the clock system needs manual configuration, the microcontroller does not start at 84 MHz automatically. The LED is on PIOB, that's the Parallel IO controller for port B, the hardware block that controls all the pins on port B. The oscillator and PLL resistors lives inside the PMC, the power management control. PLL stands for phase locked loop, which is an electronic circuit that generates a stable, higher frequency clock signal from a lower frequency reference clock. So why do we use the PMC and PLL in our code? The PMC, or power management control, is what allows us to turn on and configure the clocks for the microcontroller. Without it, the CPU and peripherals won't run at the speed we want. The PLL is used to boost the main oscillator's frequency. In our code, we configure the PLL inside the PMC to run the ATSAM3X8E at 84 MHz, which is much faster than the default startup clock. You can see it in this function. We enable the main oscillator. Here, we set up PLL with the right multiplication and division factors. And we use the main clock to use PLL so that the CPU and peripherals run at the full speed. After this setup, we can safely blink the onboard LED using the 84 MHz clock. Now, let's talk about the LED. If you go to this link and open the pinout PDF here, you can clearly see that the onboard LED is controlled through port B, or PIOB, the Parallel IO controller for port B, specifically bit number 27, also known as PB27. This LED is also connected to digital pin 13, which is what Arduino sketches usually refer to. Okay, now let's go to ATSAM3X8E datasheet. You can simply Google it. Click on the second link and open this PDF. Now, in the datasheet, we're looking for the base addresses of PIOB, PMC, and other important peripherals. If you go to page 31 of the datasheet, you can find the memory mapping section. Here, you will see the base addresses of the peripherals. For example, PIOB starts at 0x400E1000, and the PMC, the power management controller, starts at 0x400E0600. To control the LED, we need to work with 4 registers. You can find all the details about these registers on page 631 of the datasheet, in the table that lists all the memory mapped registers for the PIO controllers. These 4 registers are PIOB_PER, or PIO enable register, PIOB_OER, or PIO output enable register, PIOB_SODR, or PIO set output data register, and the last one is PIOB underscore CODR or PIO clear output data register. This table shows the offset of each register and indicates whether it's readable, writable, or both. For example, PIOB underscore PER and PIOB underscore OER are writable because we use them to enable the pin and configure it as an output. And PIOB underscore SODR and PIOB underscore CODR are also writable registers that let us set and clear the LED. The reset column shows the value that each register has when the microcontroller first powers on or resets. This matters because some registers start with useful default values while others need to be explicitly configured by our code. In the next video, I'll dive deeper into the registers and their addresses and show you how to define them in our code. For now, we're just getting familiar with this amazing chip. But here's a question. Is this all we need to get started? No. This chip needs a few more things to actually blink. In the next videos, we're going to create 3 files for our project, which are essential for a typical bare metal project on the ATSAM3X8E. These files are blink.c, startup.c, and ATSAM3X8E.ld. Blink.c, the main application. This is where the application logic lives. It configures the CPU clock, sets flash wait states, enables PIOB, sets PB7 as output, toggles the LED, and handles delays. Startup.c, startup code and vector table. This file sets up the stack, disables the watchdog, copies that data to SRAM, zeros.bss, defines the interrupt vector table, and finally jumps to the main function. Without this file, the main function never runs. ATSAM3X8E.ld, linker script. The linker script tells the compiler where to place code and data in memory, flash, SRAM, stack, and the vector table. ARM cannot run without it. And that's a wrap for today's intro to the ATSAM3X8E and the Arduino Due R3. We have explored what makes this microcontroller so powerful, a 32-bit ARM Cortex-M3 running at 84 MHz with a completely new memory map, startup sequence, and clock system compared to the 8-bit AVR. We also got familiar with the essential peripherals like PIOB, which drives the onboard LED, and the PLL and PMC, which handle the system clocks. Now you know where these registers live inside the datasheet and why they are critical for getting the chip running. In the next video, we'll roll up our sleeves and write our first bare metal C program for the ATSAM3X8E using 0 libraries. We'll dive into the blink.c file, break down every register we use, and understand exactly why each one is needed to make the microcontroller come alive. If you enjoyed this video, make sure to like, share, and subscribe if you haven't already. Hit that notification bell so you don't miss the next episode. You won't want to miss the hands-on coding adventure we have coming. Get ready to dive into real bare metal programming and take full control of the Arduino Due. See you in the next video.